So, hi everyone. My name is Zhou from Zhejiang University and NetEase Game in China. Today, I'm glad to introduce our paper, Learning a Deep Motion Interpolation Network for Human Skeleton Animations.
Yeah, Chi, can you switch on your camera just in case if it's all right? Yeah.
Oh, please wait.
That's better. Thank you.
Okay. So, motion interpolation technology produces transition frames between two discrete movements given two arbitrary motion clips, motion A and motion B. If we concatenate motion A and B directly, it will lead to discontinuous transition boundary. So motion interpolation technology like SLURP is often used to produce transition frames. It can generate smooth but unnatural transition frames. You can see the result is smooth, but it seems likely unnatural, especially on the foot joint. So in our work, we propose a data-driven method to learn the patterns of motion from real mocap dataset. And our data-driven method can generate smooth and natural transition frames. So before I introduce our architecture of the internet, of the network, I'd like to introduce the image inpainting. Actually, motion interpolation can be viewed as a problem of image inpainting. It can be viewed as completing missing motion frames within a sequence. Actually, image inpainting aims at completing missing area of the image. So the input of the inpainting question is an image with some missing area, and the output is a completed image. So we draw the idea of the image inpainting, and we can represent our motion A as an image, where the rows represent motion frames, as the columns represent quaternions of all joints. And then we can also write motion B as an image too. So the problem of motion interpolation can be converted to a question of image inpainting. So the input of the network is a missing image, and using our deep motion interpolation network, it can generate the interpolated motion. And finally, the interpolated motion can be converted back to the motion clips. And it generates a possible motion clip that can interpolate the two predefined motion clips. And finally, we can drive an animated visual character. So now I'd like to introduce our network architecture. And our network consists of a generator and a discriminator. The generator is an encoder-decoder architecture with an hourglass block. We designed this hourglass block that had multi-scale feature maps range from coarse to fine. And the hourglass network does downsample and upsample operation and combine multiple scales features with residual structure. And the relation of connected joints could be better recognized at different scales in this image. And the input of the generator in an image to be completed, it represents the motion A and motion B and the middle motion to be interpreted. And the output of the generator is a completed image. And the encoder and decoder are composed of rest block and convolution operations. And the hourglass net also make use of the residual blocks. Besides these first branch, we also apply a second branch to extract the common features of two motions and add an in layer to combine these features. The interpolation motion depends on the former motion A and the later motion B. Not only the body pose of this motion, but also their movement speed influences the result of interpolation. We use ADA in layer. It can align the mean and the variance of the embedding features of these two motions. So next we concatenate ADA in's output with hourglass networks to produce a final impinting result, where the embedding of the former of the latter motion could guide the training of the impinting network. So the next is the discriminator. We design this discriminator to determine if it is an impinting image or a ground truth image. And again, manages to truly model the data distribution of ground truth motion to generate natural looking results. The discriminator is a fully convolution network. It includes stacked convolution, batch normalization, and linear root layers. So that's the architecture of our network. And later, we need to define the loss functions. Our loss function include two main losses. One is disjunction loss, and another is adversarial loss between the impinting result and the ground truth image. The disjunction loss forces the generator to preserve the information of the original input, and the adversarial loss forces the interpreted motions more natural. And now we define Q as original motion image and Q out as an image and impinting index worst output. M as a mask image. It is a binary image that indicates the image completion mask. And the mask loss computes the L1 distance between impinting motion and the ground truth in the mask area. This loss improves the similarity of the output image and the ground truth. And besides L1 loss in mask area, we also define overlap loss of N frames near the mask area. This loss forces the network to produce a natural transition of image motion. And to smooth the impinting motion, we propose motion smooth loss. The smooth loss is sum of L1 distance between T+1 frames quaternions and T frames quaternions in mask area. And in impinting task, BP loss means boundary pixels error loss. BP loss only considers the pixel error near the boundary. So we use BP loss to make the transition more smooth too. And then we also use structural similarity loss to as an image suppress small noise in the image results. And we also use global rotation loss. We represent human pose at every frame as a quaternion vector, and to preserve 3D positions information, we use forward kinematics to compute the global rotations of each joint and compute the L1 distance between the ground truth and the impending result. And the final is the adversarial loss. It forces the interpolated motions more natural. So the final loss is the weighted sum of previous losses. So, and then we chain the network with these losses. Besides the deep motion interpolation network, we also propose a small network, because traditional motion interpolation like slurp between two keyframes must identify the number of interpolation frames. Actually, the number of frames is manually adjusted by experts after visualization. And to obtain the interpolation frame number, we propose a simple convolution neural network. It can predict the interpolation number of frames given two motions, and benefit from the fully convolutional generator and the impinting mechanism. We can change the impinting area along the frame dimension. And this figure shows the structure of adaptive impinting network. It has 3 convolution blocks with a fully connected layer. And to predict the number of interpolation frames, we mask the ground truth motions and divide the frames into 5 categories, including 5 to 85 frames. And we view this network as a classifier. And we train, and we use cross-entropy loss and train the network on our mocap data set. And the final classification accuracy in text data is 62.5. So using this small network, we can predict the frame to be interpolated. It seems like predict the distance between two movements. So I'd like to share some experiments results. First, I'd like to introduce the data sets we used. We collect the data set and using our motion capture system, and we collect 2 data sets. One in get data set including 614 human motions. And we also collect another data set, gate data set including 13 human motions from 3,000 to 7,000 frames. And we split the data set into 19% trained data and 10% test data. And each motion is represented by root position and quaternion rotations of skeleton with BVH format. And to represent valid rotations, after the prediction, we perform post-processing to normalize the interpolated quaternion to a unit vector. And for this experiment, for quantitative comparison, we fix the number of interpolation frames to 30. We could also use AIN to predict the number of frames. And I'd like to show the quantitative results. We compare our impinting result network with SLURP, and table 1 summarized SLURP and ours for quantitative comparison. For the situation when we interpolate between 2 motions, we find that SLURP actually has lower earworm loss. However, the earworm loss could not directly reflect the visual quality. Despite the lower loss, slurp generates motion sequences with same angular velocity. It only considers two keyframes, does not take the concrete motions into account, thus the motion less natural. And we also conduct an ablation study to verify the impact of each component of our proposed network and the influence of different loss function together with gain loss, as shown in this table. And then we conduct a speed comparison with another LSTM-based method. The Inpainting image length is set to 15, 30, and 60 frames, and we record the CPU model inference time. Our model could generate transition frames within a single forward inference. Thus, the computation time is frame independent and could reduce computation time for interpolation. And to verify the effectiveness of our method, we also conduct a subjective evaluation. A user study online was carried out to compare four conditions, including the slurp, our network, and ground truth. And 31 participants were invited in their user study. After watching the video, they were instructed to use 5-point Likert scale to rate the naturalness of the animation and the smoothness of the animation. And this figure shows the rated results and shows that our method is better than slurp in naturalness and smoothness. And this table shows the results of a novel test. The test shows that our method better than slurp in terms of naturalness and smoothness. So I'd like to show some video compared with slurp on the data set. And the left is interpolated with slurp methods, and the middle is interpolated using our network, and the right is the ground truth. And I'd like to share more results for our dataset compared with slurp and ours. This is the result of motion interpreted by our network. And there are more results. And that's the result on our gesture data set. Okay. compare the movement of the hand. You can see the different speed of the motion. And that's the network we proposed. So we propose this network. It is a deep learning architecture for human motion interpolation. And we view joint rotations and positions of human motion as motion images and complete missing area. And the unknown motion frame can be generated in a single model inference rather than frame by frame iteration. And the subjective evaluation shows that our motion generated by our network are more natural compared with SERP method. So that's all. Thank you for your watching.
Okay, sorry, I think thank you, Chi. So I just struggling to unmute myself. So it's a nice presentation. So I have a question coming from Leon. So that Leon, you may take the privilege as a presenter. So as you're now in the panel members, you could ask a question in audio. So would you like to do that?
Yeah, sure. Can you hear me and see me?
Yes.
Okay, so thank you for the presentation. I think it was quite cool. I like the idea of taking motion as images. I had a question about the adaptive interpolation. I mean,
Yes, I see.
It's almost 40% errors, and I think it's quite high, but also I figured the precise number of frames predicted is not that important, because maybe if the motion is, if the network predicts a motion that is 5 frames longer or shorter than the original one, it's not that big a deal. The motion will still look all right. So yeah, I was wondering if you tried computing this classification accuracy with some kind of margin. Like,
okay. Actually, the classification accuracy is a little bit high, but it's a reason because different motion frame both okay, and just two arbitrary motion clips. So if even to motion clip, motion A and motion B, if we interpolate the 13 frames, 30 frames or 40 frames, in our experiment, we find that the visual quality is both okay. So maybe this is the reason that they are both reasonable. So the classification accuracy is a little bit high.
Right, thank you.
Thank you. So we may want to take another 2 questions. So if anyone would like to throw a question, please feel free.
I have a question.
Yes, please go ahead.
So following that, the Leon's question, I'm wondering why you framed this problem as a classification rather than predicting the frame number.
Oh, actually, we also do we view the AI as a classifier, and we also view them as a regressor and in our experiments. And actually, because we find that when the frame the difference of the motion less than some number, we can see that both motion clips are both visual quality the visual quality is both okay. But so we divide the frames into 5 categories is about 20 frame margin. And it's a reason that we find that maybe the difference of the frame number are less too small. The results are both okay. So we view this as a classifier to compute the classification accuracy.
Okay, so actually I have another question. So in your framework, you use the adaptive instance normalization. I'm wondering what was the effect or benefit of using that module on top of the unit,
You mean this branch?
Yeah, right.
Yes. Because given two motions, motion A and B, maybe they have different root position and a different root position. So we use add-in layer to calculate the mean and the variance of the whole motion, and normalize them to the same mean and the same variance to decrease the effect of the different root motion.
Okay.
And we also use this branch to guide the training of the network. In the later ablation study, we show that our add-in layer has some impact, and so with add-in layer, the different losses could be decreased.
Yeah, but I see that the benefit is quite marginal. Actually, that's the reason why I asked. Anyway, thank you.
Okay.
Thank you, Chi, and thank you, Sang-hee. So I think that's because of time, I think we will move on. So, but feel free to contact Chi during the break or via email so that you can follow up